here we go. We're going to hopefully teach some stuff. We want to develop probability models using experimental and theoretical probability. We want to explain the meanings of experimental and theoretical probability. We want to find experimental and theoretical probabilities. And we want to use probability to make predictions. That's really the big point of probability, is that we don't want to live in timidity, afraid to move forward on anything. So the idea is that if we apply some probability to things, then things might not be so bad. So probability that is based on repeated trials of an experiment is called experimental probability. So notice this is repeated trials of an experiment. This is something that you actually do. So this is doing. I want you guys to know that. This is doing. This is something actually has to be done. So, and what it is it's the probability of the event. That's what P event means. It's the probability of the event equals the number of times the event occurs divided by the total number of trials. So we look over here, it says the table shows the result of spinning a penny 25 times. Now, yes, it says spinning a penny 25 times. What is the experimental probability of spinning heads? So we look over here and we want the probability of spinning heads. So this is how we write that. We go P heads, and that means probability of spinning heads. And that's going to be the number of times the event occurs, which was 6, out of the 25 times that we spun the penny. So one way to write the probability is 6 over 25. Another way is to divide 6 by 25. And when you divide 6 by 25, you get 0.24. And so another way to write the probability besides that is to also change it to a percent, which is 24%. So the probability of spinning heads is 24%. Now, down here we've got this. The table shows the results of rolling a number cube. Now, a number cube is typically a die. It's just that they don't call them dies for some reason in a lot of textbooks that I don't understand why. But we roll it 50 times. Find the experimental probability of the event. So this die gets rolled 50 times, and out of that we want to find out the probability of rolling a 3. So we look at the table, we get 8 times out of 50. So if we divide 8 by 50, that's going to give us 0.16 times by 100, and that gives us 16%. So the probability of rolling 3 is 16%. Rolling an odd number. The odd numbers are 10, 8, and 11. Or sorry, 1, 3, and 5 are the odd numbers, and there's 10 of them, there's 8 of them, and there's 11 of them. So we're going to add those numbers together, 10 plus 8 plus 11. That gives us 29. So the probability of rolling an odd is 29 over 50. And so if we divide 29 by 50, that gives us 0.58, which if we multiply that by 100, that gives us 58%. So the probability of rolling an odd number is 58%. Now notice, again, these were things that we actually did, or someone actually did, and we're looking at the data afterwards. But now it says, when all possible outcomes are equally likely, which is an important thing to think through. So things have to be fair. The theoretical probability of an event is the quotient of the number of favorable outcomes and the number of possible outcomes. So the number of favorable outcomes and the number of possible outcomes. This is pretend. We're not going to actually do this. We're going to think about what would happen if we did do it. So for instance, you randomly choose one of the letters shown. What's the theoretical probability of choosing a vowel? So instead of going and grabbing a vowel a whole bunch of times, we're just going to actually look at this and go, hey, how many letters are there? Well, 1, 2, 3, 4, 5, 6, 7. There's 7 possible outcomes. So the probability of choosing a vowel is going to be out of 7. And the vowels are A, E, I, O, U. And so some of you might go sometimes Y, so I'm not going to put in sometimes Y to begin with. So A, E, I, O, U are the vowels. And if we look then, 1, 2, 3, there's 3 vowels. So what we do is we divide 3 by 7. Now that's going to give you a repeating decimal. And we just need to work smarter, not harder on this. I'm going to go 0.429 and then multiply that by 100. The reason why I go out 3 spaces is so I can do the following. When I multiply it by 100, I can say 42.9%. So it gives me 1/10%, which is kind of nice for my accuracy. So what's the probability of randomly choosing an x? So the probability of x is 1x out of 7. So we divide 1 by 7. 1 divided by 7 is 0.14. And then that 2 behind becomes a 3. We multiply by 100. And so that's 14.3%. So again, we didn't actually pick up letters. We just examined things with our eyes and with our minds, and we said, hey, this is what could happen, and it will happen if we do it enough times. So the bar graph shows the results of rolling a number cube. Remember, a number cube is a die 300 times. How does the experimental probability of rolling an odd number compare with the theoretical probability? Well, our odd numbers, we get odd numbers 48, 50, and 49 times. So 48 plus 50 plus 49, drop a 7, carry the 1, that's 147. We got an odd number 147 times. So we look at this. Probability of rolling an odd, according to our experimental probability, is 147 divided by 300. So 147 divided by 300. 147 divide 300. That gives us 49.49, sorry, times 100. That's 49% of the time we are getting an odd experimentally. Theoretically, if we think this through, theoretically, on a die, there are 6 outcomes. Out of those 6 outcomes, there's 3 that are odd. 3 divided by 6, you hopefully know, is 0.5, and so times 100 equals 50%. So what we see is we see that the experimental probability, the experimental probability of rolling an odd is slightly less than the theoretical probability, which shouldn't concern you too much as far as things go. You shouldn't be scared or worried about your die being unfair because they're very close. So how does the experimental probability of rolling a number greater than 1 compare to the theoretical probability? So rolling a number greater than 1, so probability of greater than 1. What we need to do now is we need to add the 53, the 50, the 52, the 49, and the 48. So I'm going to do that off screen on my calculator. So 53 plus 50 plus 52 plus 49 plus 48. That's 252 out of 300. So we take 252, divide by 300. That gives us 0.84 times by 100, and that's 84% of the time we're getting a number that's greater than 1. Well, theoretical probability for greater than 1, we know that there's 6 possible outcomes, and there are 5 numbers greater than 1 on a number cube. So we have 5 divided by 6. 5 divided by 6 is 0.83 repeating. So I'm going to actually write that as 8.33 repeating, because remember, we're multiplying that by 100. And so what that does for me is it gives me 83.3 repeating percent. And as we can see again, how do they compare? They are very close together. So these values are very close. Our experimentation is showing that our die is a fair die. So using experimental probability, a bag contains 50 marbles. You randomly draw a marble from the bag, record its color, and then here's an important phrase, replace it. So there's always going to be 50 marbles in the bag whenever you pull a marble out. The table shows the result after 30 draws. Predict the number of red marbles in the bag. Okay, so after 30 draws, we have picked 90 marbles. So we're going to predict. A couple different ways to do this. But the one that explains the idea the best is to go, okay, the probability of choosing a red, this is experimental probability. Experimental probability of choosing a red is 9 over 30. So 9 divided by 30 gives us 0.3 times 100, and we get 30%. So what we can do is we can say red is 30% of 50. Now again, this is just a guess based off of what we've done. So we look here, red is, so R equals 30% of 50. So 0.3 times 50 gives us 15. So we're predicting 15 red marbles. Again, there is another way to do this. What you could have done instead is you could have just said 9 to 30 equals x to 50. And then you can cross multiply. And when you do that, 9 times 50 is 450. 30 times x is 30x. We divide both sides by 30. And so x is 15. So we get 15 red marbles that way too. Good night. Good night. So last one, the theoretical probability of winning a bobblehead when spinning a prize wheel is 1/6. The wheel has 18 sections. So how many sections have a bobblehead as a prize? So we know that 1/6 of 18 are these bobbleheads. So 1/6 of 18 equals 3. So 3 sections will have a bobblehead. The prize wheel is spun 540 times. About how many bobbleheads do you expect to be won? Okay, so we know that the probability of winning a bobblehead is 1/6. So we're going to say that 1/6 of those 540 times that it's spun, we're going to get a bobblehead. So 540 divided by 6 is 90. So we're going to expect 90 times. So let me just put this into practice for a moment. Let's say that you're the one hosting a little carnival fair where you win a bobblehead if it lands on one of these 18 sections. You expect that there will be 500 people who come. So if you expect 500 people to come, you know that you're going to need you're going to need at least you're going to expect to at least need 90 bobbleheads this way. So this is just a thought for how to use theoretical probability in a meaningful way. So again, we've talked about experimental and theoretical probability. Experimental, we get experimental probability by doing things. Theoretical, we get theoretical probability by pretending things or thinking things through. And both are useful. And when things are fair, both are very close to what we predict, or when we can actually predict theoretical probability. Some things we can't predict theoretically or very easily theoretically, but we can do experimentally. And then down here we see that we can use experimental probability or theoretical probability to make predictions to help us actually move forward on various other things in life. All right, those are your notes.